Okay, let's unpack this. We are diving deep today into what might be the most familiar, yet uh, consistently misunderstood force in the universe: gravity.
Mm.
I mean, we feel it every single second, but I think very few people truly appreciate the precision of its underlying mechanics.
It's the ultimate connector, isn't it? It all
Wow.
starts with that perfect revolutionary moment. Sir Isaac Newton,
The apple.
the apple. He's looking up at the moon, orbiting, then he looks down and sees an apple fall from a branch.
Right.
His genius wasn't just observing it.
Right.
It was realizing that the pole causing that small downward motion of the apple is precisely the same force that locks the moon into its massive orbit around our planet.
It's just one unified law.
One law for everything, from the terrestrial to the celestial. It's beautiful.
And that synthesis, that idea that this universal law applies right here on your desktop, that's the foundation for our whole deep dive today.
Mm.
Our sources are fantastic. They take us right from the foundational math, how mass and distance interact, to the subtle consequences, like why you feel heavier in an elevator.
Or why the moon, which is tiny compared to the sun,
Mm-hmm.
completely dominates our planet's tides. That's a great one.
Yeah. We're also going to spend some time analyzing the subtle but really powerful effects of gravity. We've got real-world measurements taken during solar eclipses.
Another occultation, yeah.
And we're even going to get into the terrifying orbital chaos that would happen if the sun were to just, vanish for a few days.
It gets pretty wild.
So our mission is simple: strip away the misconceptions and give you the mechanical knowledge that governs everything from your weight on Earth to the speed limit of the cosmos.
Okay, yeah. If we want to move past just general concepts, we really have to start with the formula itself. Newton's universal law of gravity.
Right.
And the definition is it's so elegant. Every mass attracts every other mass. That's it. The attraction is mutual and it's calculable.
Okay, so we've got the player's two masses, M1 and M2. But what determines the intensity? How strongly are they actually pulling on each other?
That pull, the force, F, it's determined by two main factors. And they interact in pretty different ways.
Okay.
First, and this is the most intuitive part, the force is directly proportional to the product of the two masses.
So bigger things pull harder.
Exactly. If you double the mass of the Earth, the force of attraction on a satellite just doubles. If you somehow manage to double the masses of both of them, the force quadruples.
And that's why the sun, with its just staggering mass, completely dominates the solar system.
It's the king. But that part, as you said, makes perfect sense. The second factor, distance. That's where the real surprise and all the counterintuitive stuff about gravity comes from.
The inverse square dependence.
The inverse square dependence. It's not just how far apart you are, it's how far apart you are, squared.
Which means the force drops off incredibly fast.
Exactly. This is the mechanism that ensures the force just plummets as distance increases. So formally, the force F is inversely proportional to the square of the distance, d, between the centers of the two masses. So F is proportional to 1 over d squared.
Closeness is everything.
Immensely powerful in this equation.
Let's use that classic analogy, the paint spray one, to really visualize what this inverse square rule means.
Oh yeah, that's a perfect way to picture it. Okay, so imagine you're standing, say, 1 unit of distance away from a can of spray paint.
Okay.
The paint particles hit a surface with a certain thickness, a certain intensity. Now, you step back to 2 units of distance. The exact same amount of paint is now spread out over a surface area that is 4 times larger.
So the paint layer is only 1/4 as thick.
Precisely. And the reason it's 4 times larger is it's pure geometry. It comes from the surface area of a sphere.
Right. If you imagine that force radiating out spherically, the surface area it has to cover at any radius r is 4 pi r squared.
That's the one. And because that area scales with the square of the radius, the intensity of the force has to decrease in the same way.
So if you go 3 units away.
It's spread over 9 area units. The intensity is only 1/9 of what it was at the start. This really rapid drop-off is why gravity, even though it's universal, feels so weak, unless you're right next to something, astronomically huge.
And it's also why we don't feel the gravitational pull of the person standing next to us. It seems like we should, right, if it's universal.
Well, that brings us to the third and really critical component, the universal gravitational constant, which we just call G.
The fudge factor.
Sort of, yeah. It's this tiny, subtle number that converts the proportionality into a full, usable equality. So F equals G times M1, M2 over D squared. And when I say tiny, I mean tiny. It's 6.67 times 10 to the minus 11.
That number is it's staggering how small that is. What does that actually imply for us in everyday life?
It implies that unless one or both of your masses is truly astronomical like the Earth, which is around 6 times 10 to the 24 kilograms, the resulting force is just vanishingly small.
It's the weakest of the fundamental forces.
By far. If you take two bowling balls, say 7 kilograms each, and you put them 1 meter apart, the gravitational force between them is around 3 times 10 to the minus 9 newtons.
Which is nothing.
It's about a billionth of the force it takes to just pick up one of those balls. It's there, but you'll never, ever feel it.
And measuring that tiny force, that was a huge deal historically.
Oh, massive.
Yeah.
It took Henry Cavendish in the 18th century with his torch and balance experiment. He was measuring this minuscule attraction between lead spheres.
And in doing that, he was basically weighing the Earth, right?
He was. By figuring out the value of g, he could then calculate the mass of the entire planet. It's one of the great feats of experimental physics, proving these universal laws apply right here in a quiet lab.
So for practical stuff, like calculating my own weight, we really only care about the force from one massive object, the Earth.
Exactly. So let's do that. Let's calculate the pull of gravity right here on the surface for a standard object, say 1 kilogram.
Okay, so we plug in the Earth's mass, and for the distance d, we have to use the Earth's radius because it's measured from the center of mass.
Right. And when you plug all those numbers in Earth's mass, the radius of about 6.4 times 10 to the 6 meters, and that tiny g, the force, F, comes out to approximately 9.8 newtons.
And we often simplify that to F equals mg, where g is the acceleration due to gravity.
Yep. And that force, F, is precisely what we define and what we experience as our weight.
Okay, so now we have that baseline. Let's bring back the inverse square law. Let's see how much that force actually diminishes when we move away from the center of mass, even just a little bit.
Classic example.
Let's climb Mount Everest, 8,850 meters high. You are undeniably farther from the center of the Earth.
You are. But this is where the sheer scale of the Earth really matters. You start with a radius of 6,400,000 meters.
Okay.
By climbing to the peak of Everest, you're adding a mere 8,850 meters to that. Your new total distance is 6,408,850 meters.
So as a percentage, that's a tiny, tiny change.
It's minuscule. And when you square those two distances and look at the ratio, the result is, well, it's pretty counterclimactic.
You're higher than anyone on Earth, but the pull of gravity on you is only, what, 0.997 times what it was at sea level?
That's it. For a person who weighs 200 pounds at sea level, the force on them at the summit is reduced by only about 0.6 pounds. They'd weigh 199.4 pounds.
So if anyone tells you they lost weight on Everest, it was probably just dehydration.
Not the physics, no. But it does demonstrate the law perfectly. The distance change is so small compared to the planet's size that the force drop-off is practically negligible at altitudes we can actually reach.
Right. And moving from that sort of static pull on a mountain, we get into the world of dynamics. And this is where the sensation of gravity changes dramatically.
Yes. And this forces us to get a little more precise with our definition of weight itself.
So initially we said weight is the force of gravity, F equals mg. But that definition kind of breaks down the moment you start accelerating because your feeling of weight changes.
That's exactly right. The way physics describes the felt sensation, the weight you feel when you stand on a scale, is actually the force exerted against a supporting surface.
You are literally as heavy as you feel.
Yes. The scale isn't measuring gravity directly. It's measuring how much its internal spring is being compressed by the force required to keep you from falling.
And the classic elevator ride perfectly demonstrates this. Gravity hasn't changed, but your felt weight is all over the place.
Exactly. Think about the start of the ride. When the elevator accelerates upwards, the floor has to push up harder on your feet to get you moving up.
Harder than just holding you still.
Right. So the floor pushes harder, the scale reads a higher support force, and you feel heavier.
And then the opposite when you go down.
When it starts accelerating downwards, the floor doesn't need to push as hard. The required support force goes down, the scale reads a lower weight, and you feel lighter. Your actual gravitational force, m-brang, hasn't changed at all. Just the support force.
So the magic moment is when that support force drops all the way to zero. That's how we get true weightlessness, even though gravity is still there.
That is the state of free fall. The moment that supporting structure, the elevator floor, your chair, or whatever, is removed and you start accelerating downwards only under the influence of gravity, your weight under this felt definition becomes zero.
But gravity is still pulling you down.
Still pulling you at 9.8 meters per second squared. But since nothing is pushing back up on you, there's no support force, and therefore no sensation of weight.
This idea is so crucial when we talk about space. You know, the Vomit Comet, that plane that flies in a big arc.
Yep, it's just creating temporary free fall. It's the closest most people get to experiencing what astronauts do.
And it perfectly illustrates the big misconception. When astronauts are in orbit on the International Space Station, they are not in zero gravity.
Not even close.
Yeah.
They are in a state of continuous free fall. Everything inside that station, the tools, the coffee, the astronauts themselves, is constantly falling around the Earth altogether.
Okay, I want to pause on that phrase, falling around the Earth. Because if you're falling, you should eventually hit the ground. How does continuous falling become an orbit?
Think of Newton's famous thought experiment. Imagine firing a cannonball horizontally from a super high mountain.
Okay.
If you fire it slowly, it falls and hits the ground pretty quick. Fire it a bit faster, it goes farther before it hits. But at a certain really high velocity, the curvature of the Earth falls away from the cannonball's path at the exact same rate the cannonball is falling due to gravity.
So it's still accelerating downward.
Constantly. But it never actually gets any closer to the ground. That is an orbit. It's just continuous, high-speed, controlled freefall.
And that brings us to the numbers. Since gravity follows the inverse square law, the force on the shuttle in orbit must still be significant, right?
Absolutely significant. Let's quantify it. Low Earth orbit is typically around, say, 200 kilometers above the surface.
Right.
The distance d in the formula is from the center of the Earth. The Earth's radius is about 6,370 kilometers. So when the shuttle's on the ground, d is 6,370. In orbit, it's 6,370 plus 200. So 6,570.
Okay, so the change in distance is only about 3% of the total distance from the center. And since we square that in the formula, the force reduction should be pretty minor.
It's surprisingly minor. The gravitational force on the shuttle in orbit is still a whopping 94% as much as it was sitting on the launch pad.
94%.
Yeah. The idea of zero gravity is purely linguistic. They are experiencing weightlessness because there's no relative support force, but the force of gravity is almost the same as it is down here.
And understanding that is fundamental for satellite mechanics, for space travel.
Absolutely. You need rockets to fight atmospheric drag, but you don't need thrust to stay in orbit. Gravity handles that part for you beautifully.
This idea of continuous freefall, or maybe continuous acceleration, is a perfect bridge to our next topic, because tides are caused by different parts of an object accelerating differently.
Tides are maybe the most misunderstood daily phenomenon related to gravity. We all know the moon causes them, but the explanation usually just stops there. The real mechanism, it hinges entirely on this concept of differential gravity.
Okay, let's nail down that definition before we move on. What is differential gravity?
It's just the variation in the gravitational pull across a really big object like the Earth. Since gravity obeys that inverse square law, the side of the Earth closest to the moon is pulled with a significantly greater force than the center of the Earth is.
And the center is pulled harder than the far side.
Exactly. It's the difference in force, the gradient, that causes the tides.
So we're not talking about a single unified tug on the whole planet. We're talking about a subtle stretch.
Precisely.
Mm.
If the force were equal everywhere, the entire Earth would just accelerate towards the moon uniformly. The oceans wouldn't move relative to the crust. But because the force varies, the planet gets elongated along the axis that points toward the moon.
And that elongation is what creates the two bulges. One on the side closest to the moon, which is pretty intuitive.
Yep.
And one on the side farthest away, which is often less intuitive.
Right. So the bulge on the near side is created because the moon is pulling the water away from the main mass of the Earth. The bulge on the far side, though, is created because the moon is pulling the main mass of the Earth away from the water on the far side. That water is essentially left behind, forming a second bulge.
So the Earth gets stretched like a ball of jello.
That's the perfect analogy.
And the rhythm of the tides, the high and low tides, that just comes from the Earth spinning underneath these relatively fixed bulges.
Yes. As the Earth does its rotation every 24 hours, any spot on the coast passes through both of those tidal bulges. That gives you 2 high tides and 2 low tides every day.
And the average range is actually pretty modest in the open ocean, right? About a meter.
Around a meter, yeah. The spectacular, really huge tides you see in places like the Bay of Fundy, that's all due to topographical funneling, the shape of the coastline.
We also know that the cycle shifts a bit every day.
Right, because while the Earth is spinning, the moon is also moving in its orbit around the Earth. So it takes the moon an extra 50 minutes to get back to the exact same relative spot in the sky.
Which means the time of high tide shifts forward by about 50 minutes each day.
Correct.
Okay, now let's tackle the grand tidal paradox, the one that really messes with your intuition. The sun. It's massive. Its total gravitational pull on Earth is about 180 times larger than the moon's. So why aren't solar tides 180 times stronger? Why are lunar tides actually twice as strong as solar tides?
This is that critical moment where we have to apply the lesson of differential gravity. The reason the sun loses the tidal battle is its distance. The sun is 390 times farther away than the moon.
Okay.
And because of that extreme distance, that 1 over d squared term in the gravity formula gets really smooth. It flattens out across the Earth's width.
So let's break down the numbers to see how big a deal that distance factor is.
Okay, for the sun, the difference in its gravitational force between the near side of the Earth and the far side is tiny. It's only about 0.017% of the total force. The stretching effect is minimal.
And now contrast that with the moon, which is so much closer.
The moon is close enough that the differential pull across the Earth is huge, relatively speaking. The difference in the moon's pull at opposite points on Earth is a massive 6.7%.
Wow. So we take the sun's big force advantage, the 180 times, and we multiply it by its tiny difference factor, the 0.017%,
And you get a resulting tidal force of only about 3%.
which is roughly half the moon's 6.7%.
Exactly. The moon is the tidal champion, not because its overall pull is stronger, but because its closeness makes the gravitational gradient across the Earth so much steeper. Distance is everything for tides.
But the sun and moon aren't always fighting each other. Sometimes they align, and that creates what we call spring and neap tides.
Right. So when the sun, moon, and Earth all line up in a straight line, which happens during a full moon and a new moon, their tidal forces combine, and they amplify each other.
This gives us the highest high tides and the lowest low tides, the spring tides.
Exactly. And spring here means to spring up. It has nothing to do with the season.
And neap tides are the opposite, when they're pulling at right angles to each other.
Right. Neap tides happen during the half-moon phases. The moon is trying to make a high tide, but the sun is trying to pull the water away at a 90-degree angle. They partially cancel each other out.
Resulting in a much smaller tidal range, lower high tides.
A much more mellow tide, yeah.
And this stretching phenomenon, it's not just limited to the liquid oceans, is it?
Not at all. The entire planet is elastic. The molten Earth, with its thin crust, also experiences what we call Earth tides. The solid ground actually rises and falls by about 1/4 of a meter twice a day.
We don't feel it, but it's happening.
It's happening. And some sources suggest that this physical stretching, especially during the maximum strain of a spring tide, can put extra stress on fault lines, which might subtly increase the likelihood of earthquakes or volcanic eruptions.
Wow. And our atmosphere experiences tides, too.
Atmospheric tides are very real, though they don't really matter to us on the ground. High up in the ionosphere, the movement of charged air particles from the tidal force creates these complex electric currents and magnetic tides. It actually influences things like radio propagation.
Okay, let's answer the personal question. If the whole planet is stretching, why don't we see tides in, say, Lake Michigan? And why aren't the fluids in my body sloshing around?
It comes back to that need for distance for a differential pull. A lake, even a huge one, is just too localized. There's no significant distance variation between the part of the lake closest to the moon and the part farthest away.
So no stretching happens.
No stretching across its basin.
Yeah.
The water level just rises and falls with the earth tide passing underneath it.
And for the human body.
You're simply not tall enough?
Yeah.
The difference in gravitational pull between your head and your feet from the moon is completely negligible. It's actually a fun calculation.
Oh, yeah.
The tidal effect from the moon on the fluids in your body is less than the tidal effect you'd get by just holding an apple about a half meter over your head.
That's incredible.
Your height is just not an appreciable fraction of the Earth's radius, so the differential pull is basically zero.
Okay. As we shift from this familiar Newtonian world to the extremes, we have to acknowledge that our understanding has evolved a bit.
It has. While Newton's law is an excellent approximation for most things in the solar system, it needed some refinement for, massive objects and really high speeds.
Newton's idea was that gravity was a force acting instantaneously. If the sun moved, the Earth would know about it right away.
That assumption was a problem. We now model gravity as a gravitational field that exists around every mass. But the real revolution came with Einstein and general relativity.
It's GR.
GR, which basically replaced the concept of a gravitational force with the geometric idea of warped four-dimensional spacetime. Mass doesn't pull on other masses. It curves the fabric of space-time, and other objects just follow those curves.
And while our sources don't require us to get into the weeds of GR's math, the theory gave us one absolutely critical universal truth: the speed of causality.
Precisely. If mass warps space-time, that ripple cannot travel instantaneously. GR established that any gravitational influence, any change in the field, propagates at the universal speed limit.
The speed of light.
The speed of light. That's the speed of causality. No information can travel faster than that.
Before we get to the ultimate limit, the black hole, let's just touch on the internal structure of gravity inside a planet. It's probably the least intuitive concept we've hit so far.
It's a great thought experiment. If you could drill a frictionless tunnel straight through the center of the Earth and drop something in, what would happen?
Your intuition says gravity should get stronger as you get closer to the core.
Right. But the sources tell us it's the exact opposite. The gravitational field strength actually increases linearly from the center outwards. It's at its maximum at the surface.
And right in the middle, the force is zero.
Zero. Because of symmetry. As you tunnel inward, the mass above you starts pulling you backward, canceling out some of the pull from the mass below you. When you reach the exact center, you've got equal mass pulling you in every single direction.
And all those forces cancel out perfectly.
Perfectly. So an object dropped in would just swing past the center, slow down, get pulled back, and it would just oscillate back and forth, like a mass on a spring.
Okay, so speaking of gravity reaching its maximum, black holes, the ultimate extreme. They form when massive stars, we're talking 1.5 times the mass of our sun, and way up when they run out of fuel.
Right. They can no longer fight their own gravity, and the star collapses catastrophically. The core condenses into these incredibly dense states. It might stop as a neutron star, where gravity has literally crushed electrons into protons to make neutrons.
And the density of a neutron star is just, it's mind-boggling.
Oh, it's insane. We're talking densities of 10 to the 18 kilograms per cubic meter. A single teaspoon of that material would weigh 50 billion tons here on Earth.
And if the star is even more massive, the collapse just keeps going.
It continues right past that neutron star limit. The surface gravity becomes so immense that the escape velocity, the speed you'd need to break free, exceeds the universal speed limit. It exceeds the speed of light.
And that's when a black hole forms. Nothing can escape.
Not light, not matter, nothing. The boundary around that region where the escape velocity equals the speed of light, that's what we call the event horizon.
Okay, so now we get to that wonderful hypothetical scenario. If the sun were instantly replaced by a black hole of the exact same mass, what happens to the Earth?
This is the perfect test of physics versus intuition. Your intuition screams, we get sucked in immediately.
Right.
But we have to trust the equation. F equals G times m1 m2 over d squared. The force depends only on the masses and the distance between them.
And we said the black hole has the exact same mass as the sun. How the distance is the same.
So the gravitational force F would not change, not one bit.
Meaning the Earth would just continue circling in its perfectly normal orbit, completely unaffected by the sun's new density.
Exactly. The only immediate effects would be that 8 minutes after the sun vanished, we'd see the light go out. And we'd also feel the change in gravity then, because it takes 8 minutes for that information to reach us. But we just keep on orbiting.
That's comforting in a very weird way. And since we can't see black holes, that gravitational influence is how we know they're there.
That's how we detect them. We watch their extreme gravitational influence on neighboring stars, or we track the stars orbiting those colossal black holes at the centers of most galaxies.
Let's pull back now from the hypothetical vanishing sun to a very real, very measurable instance of solar occultation, a solar eclipse. The gravitational effects are negligible, but the atmospheric and meteorological effects of that sudden shading, they're profound.
Yeah, our sources detail a deep dive into the 2015 solar eclipse, which produced a pretty significant partial occultation, about 66 to 70% over Switzerland.
And it was a gold mine for researchers.
Oh, perfect natural experiment. The atmosphere was clear, so they could isolate the effects of the shading on weather systems using this huge network of 184 weather stations.
Okay, so what was the most immediate, easily measured consequence?
Temperature drop. By blocking 70% of the sunlight, the energy input to the ground just stopped. The researchers calculated an average temperature drop across all 184 sites of 1.51 Kelvin.
Which doesn't sound like a huge number, but it was statistically significant across the whole region.
Exactly. But the variability was huge. And that suggests that local geography matters a whole lot more than the event itself.
How so?
Well, while the average was 1.5 Kelvin, The most extreme drop they recorded was a chilling 5.8 Kelvin, almost 4 times the average. And that was at a single mountain site located inside a sharp topographic depression.
A bowl, basically, where cold air could just pool.
A natural cold trap.
Yeah.
The study concluded that the local setting, whether you're on a peak, in a valley, or in a basin, is the single most important factor for how much the temperature will drop at any one spot.
And how does that 5.8 Kelvin drop compare to historical eclipses?
It's high for a partial. The historical average, going back to 1834, is about 2.6 Kelvin. The absolute extremes are up to 11 Kelvin, but that's during a full totality. So even 70% shading in just the right or wrong location can really replicate the cooling effect of a much bigger eclipse.
And that rapid localized cooling has to mess with local wind systems, especially in a mountainous place like the Alps.
Oh, it wreaks havoc on what are called thermotopographic winds. These are local winds, like valley breezes, that are driven by these small temperature differences between sunny slopes and shaded valleys.
And the eclipse happened at just the right time to interrupt that.
It coincided precisely with the typical morning transition, when the nighttime downbeat winds, which are driven by cooling, normally switch over to the daytime up-valley winds, which are driven by heating.
So what happened to that switch?
At one specific site, the transition to the daytime up-valley wind was delayed by about a full hour. It just paused the daily cycle.
Wow.
And even more dramatically at another site, the shading prevented that daytime up-valley wind from ever even starting. The colder, denser down-valley wind just persisted for hours longer than it should have. The eclipse basically froze the local weather system in place.
And this specific reaction,
Yeah.
it gave them a rare chance to test two competing theories about large-scale wind patterns around an eclipse shadow, right?
This is where it gets really fascinating. For over a century, the main model, the Clayton theory from 1901, predicted that the cold air at the eclipse center should flow outward in an anticyclonic, so clockwise pattern, for up to 2,400 kilometers.
Which would have easily included all of Switzerland.
It would have. But a revised model from 2003 by Applin and Harrison suggested a smaller anticyclonic core, only about 1,600 kilometers. That would have placed Switzerland, which was 2,000 kilometers away, in the outermost zone of cyclonic flow, counterclockwise.
So which was it? A huge cold outflow or a cyclonic transition zone?
The study found a significant and consistent preference for cyclonic rotation in the air currents, especially at an elevation between about 1,700 and 2,700 meters.
And that elevation is key.
It's key because it's high enough to get away from the messy influence of trees and houses and stuff on the ground. It gives you a clean measurement, and that data lent really strong support to the newer Applin and Harrison model. It actually updated our understanding of how these eclipse weather systems circulate.
So when we talk about the absence of light, we can move beyond just physics and into some really specialized areas. There's a whole field called scotobiology.
Right, scotobiology. The study of the biological effects caused specifically by darkness, which is different from just the absence of light.
That's the distinction that often gets missed, I think. Darkness isn't just a passive state. It's an active ingredient for life.
It's a critical biological imperative.
Yeah.
I mean, for animals, it dictates the timing for foraging, breeding cycles, migration. In humans, that light-dark cycle regulates our circadian rhythms, our immune system, hormone release.
And the most counterintuitive insight from this field is about how plants measure time. It flips the classic terminology right on its head.
It completely changes how we talk about it.
Yeah.
Plants have evolved not to measure the length of the light period, but to measure the length of the uninterrupted dark period. A plant we used to call a short day plant is actually a long night plant.
Meaning it needs a minimum amount of continuous darkness to trigger things like flowering.
Exactly. Which means that even a brief flash of light in the middle of the night can trick the plant into thinking the dark period was too short.
And that's the danger of light pollution.
Precisely. That brief, low-level light can interrupt that critical process, and it can stop plants from reproducing or preparing for winter. It's a powerful example of how the simple removal of light is an active, timed signal.
Shifting to another area where this kind of occultation is a daily problem, satellite communications. Satellites in orbit deal with two distinct types of solar interruption.
The first is a classic eclipse for the satellite itself. This is where the Earth or the Moon blocks the sunlight from hitting its solar panels. We just call it a satellite eclipse.
And since solar panels are the main power source, that means the satellite has to switch to batteries.
Correct. It immediately switches to its onboard standby batteries. And while they're designed for this, every charge-discharge cycle degrades the battery a little bit, which shortens the satellite's total service life.
Then there's also thermal stress.
A huge amount of thermal stress. Rapid heating and cooling as it enters and exits the shadow. It's a major risk factor for failure.
But the thing that causes way more disruption for us on the ground isn't the satellite being dark. It's when the sun lines up directly behind the satellite.
That's the sun transit outage, or just sun outage. It happens twice a year for a few days around the equinoxes. The geometry is perfect.
Yeah.
The sun, the geostationary satellite, and the receiving antenna on Earth are all in a perfect line.
No, why is that a problem? The sun isn't blocking the signal.
The problem is noise. The sun is an incredibly intense radiator of thermal noise, especially at the microwave frequencies that satellites use.
Oh, so when the antenna is pointed at the satellite, it's also pointed directly at the sun.
And the sun's noise is just so much louder than the satellite signal. It's like trying to hear a whisper in the middle of a rock concert. The sun acts like a massive radio jammer.
And it just swamps the signal completely.
Completely. You get signal degradation, a higher error rate, or, in the worst case, a total loss of the signal. The outage can last for up to 10 minutes a day for about 6 days in a row.
And this isn't just a technical quirk. This has real economic impact.
Oh, for sure. Stock exchanges in India, for example, have in the past had to briefly halt trading during these known outage periods to ensure fairness, so that data disturbances don't mess up the markets.
So to understand how engineers deal with this, we need to touch on two basic concepts in satellite comms. First, the Doppler effect.
The Doppler frequency shift, yeah. Since the signal is an electromagnetic wave, any relative motion between the satellite and the receiver on Earth will compress or stretch the wavelength.
Which changes the frequency you receive.
Exactly. And only the motion directly toward or away from you, the radial component, causes this shift.
This is a massive issue for low Earth orbit constellations like Starlink, where the satellites are just whipping overhead.
Absolutely. LEO satellites are always moving rapidly relative to the ground, so you need really sophisticated tracking and signal processing to adjust for that constant frequency variation.
But for geostationary satellites, which are stationary relative to the ground, it's pretty much a non-issue.
Almost negligible, yeah. Unless your receiver's on a jet or something.
So the ultimate test of a system's resilience against something like a sun outage comes down to the link budget. This is the big calculation to see if your signal is strong enough.
The link budget is the absolute cornerstone of satellite engineering. It's the calculation that determines the total power received, P sub R, by the Earth station.
And it's usually expressed in decibels.
In dBW, yeah. The core formula is pretty simple. The received power equals the EIRP plus the receiver antenna gain minus the path loss.
Okay, so EIRP is the transmitted power, the antenna gain is how well the receiver focuses, and path loss is just the signal getting weaker over distance.
Well, EIRP is a little more than just transmitted power. It stands for effective isotropic radiated power. It's a measure that combines the actual transmitter power with the focusing power, or gain, of the satellite's transmitting antenna.
Right, and the path loss. That's where the inverse square rule comes back in, right? Even for radio waves.
That's where it comes back. Path loss is mostly determined by the distance the signal travels and its wavelength. The signal spreads out spherically and gets weaker with distance squared. And for GEO systems, that path loss is substantial. It can be over 200 dBs. A tiny fraction of the power actually reaches Earth.
But the critical factor during a sun outage isn't just the signal power, it's the noise.
That's the whole game. Engineers have to calculate the system's noise temperature to figure out the total noise power. And that lets them calculate the single most important metric, the carrier-to-noise ratio, or C over N.
And the whole link budget has to be designed to make sure that ratio is always high enough, even during known interference events.
Exactly. You need to make sure your signal is always comfortably above the noise floor.
We're going to return now to the ultimate thought experiment, the Ragnarok scenario. What if the sun were simply erased from existence for exactly 3 days, 72 hours, and then just popped back into being? And let's for a minute ignore the immediate freezing temperatures and focus purely on the orbital chaos.
This is where that speed of causality from general relativity is absolutely vital. The gravitational influence travels at the speed of light. So since Earth is about 8 light minutes away from the sun, We wouldn't even know the sun had vanished for a full 8 minutes.
And at that 8-minute mark, the gravitational tether just snaps. And the Earth, following Newton's first law, starts traveling in a straight line tangentially to its old orbit.
And our orbital velocity is high. It's about 29.78 kilometers per second. So now we have to calculate the drift.
Okay, 3 days is 259,200 seconds.
Right. So traveling tangentially at that speed, the Earth would drift 7,718,976 kilometers from its original path.
7 million kilometers sounds like a huge distance, but when you compare it to our total distance from the sun, 150 million kilometers, it almost seems recoverable.
That's the really misleading part. The new distance from the sun, when it reappears, would be about 150.16 million kilometers. That extra 160,000 kilometers is pretty minor compared to the 5 million kilometer variance we already have in our orbit.
So what's the real problem?
It's the velocity. That's what causes the catastrophe.
How does retaining our original velocity, while being slightly farther out, destabilize the orbit so badly?
Well, when the sun reappears, the Earth is angled about 3 degrees away from it, and it's moving too fast for its new, farther out position. That original velocity was perfectly calibrated for a 150 million kilometer orbit. Now, at this new distance, that velocity is way too high to maintain anything close to a circular orbit.
So the whole thing gets thrown out of equilibrium. What happens to the shape of the orbit?
The change would be catastrophic. The eccentricity of Earth's orbit, which is the measure of how much it deviates from a perfect circle, would nearly quadruple. It'd go from about 0.016 to around 0.06.
And this new, much more elliptical orbit would swing the Earth between, what, 141 million kilometers and 159 million kilometers.
Exactly. It would pass far closer to the sun and swing far farther away than it does now. And that completely disrupts the habitable temperature range. We'd get extreme heating, then extreme cold.
And that eccentric orbit would be unstable over the long term.
Highly unstable. It would make us much more susceptible to gravitational nudges from Jupiter and the other planets, leading to even worse chaos down the line. A stable orbit needs an almost perfect balance of velocity and distance, and 3 days of drifting just completely destroys that.
And now let's bring back the reality of the thermal consequences. 72 hours of absolute darkness.
The heat loss would be instantaneous and rapid. The oceans would act as a huge heat reservoir, so that would slow things down a bit, but the temperature drop would be much faster than a normal day-night cycle.
And photosynthesis would just stop.
Stops globally.
Yeah.
The entire food web collapses pretty quickly.
How quickly would the Earth actually freeze?
The ground would freeze solid within days. Within a couple of months, the surface of the oceans would freeze solid. Life might, persist in deep-sea thermal vents, shielded by the ice, for maybe 1,000 years. But the surface world would be a hard, frozen wasteland.
And even with the sun back, the long-term prognosis is bleak.
The atmospheric collapse is the final nail in the coffin. Without constant heating, the atmospheric gases would slowly freeze and fall onto the surface. Cosmic radiation would seep in. Earth would be left a dark, frozen, uninhabitable wasteland, drifting wildly on that new, unstable orbit.
It really underscores that the stability we take for granted it's not a given, it's a prerequisite for life.
It's everything.
This deep dive has covered just vast territory, from the tiny constant G to the dynamics of black holes. If we distill the most important aha moments, the 3 takeaways I really hope stick with you are: 1, gravity travels at the speed of light. 2, the power of tides comes from the difference in pull across a body, not the absolute pull. And 3, the weightlessness you see in orbit is not the absence of gravity. It is the continuous high-speed falling of objects around a planet.
And if we connect that to the big picture, the stability of our solar system is it's terrifyingly fragile. We saw that even a partial eclipse causes measurable changes in wind patterns. A brief removal of the sun causes these cascading orbital effects. Every single element is perfectly balanced.
It makes you really appreciate that 9.8 newtons keeping your feet on the floor.
Absolutely. That stability is everything.
So to end this deep dive, let's go back to that most counterintuitive finding. We established that the gravitational field inside a planet is 0 right at the center, and an object dropped through a hole would just oscillate back and forth. This raises a question for you, the learner, to consider.
Ooh, I like this.
If you could safely travel to the exact center of the Earth and experience absolute weightlessness with mass pulling equally on you from every single direction, would that sensation of balanced, symmetrical pull feel like pure rest? Or would the constant equal tugs on all sides feel like a form of extreme pressure, something to mull over until our next deep dive?